Hello, everybody. It's 1 minute past the hour, so welcome to the ENLA seminar. I'm Alex Townsend from Cornell University, and I have the pleasure today to introduce today's speaker. First, let me just remind you that during the talk, you're welcome to ask a question at any time. You can do this in two ways, either by typing in the Q&A box on Zoom, or by typing in the chat window on Zoom. Oh, and in addition, you could also type into the live chat window on YouTube. And we will be monitoring your questions for the speaker so that we can ask them at an appropriate time. Okay, so today's speaker is Nick Trefethen. As many of you know, many of you will be aware of the problem of fitting polynomials to data by means of a Vandermonde matrix, and how this can be a notoriously unstable algorithm. Today, we have the honor to hear from Nick Trefethen on how to fix this problem. Nick is a professor of numerical analysis at the University of Oxford. He's a fellow of the Royal Society. He's a member of the United States National Academy of Engineering and a global distinguished professor at NYU. In addition, Nick has many honors and awards, but the latest one is the John von Neumann Prize this year, which comes with the John von Neumann lecture at the SCIEM annual meeting, which I guess will be online this year. So Nick, I'm eager to hear about your clever use of Arnoldi orthogonalization.
Okay, shall I go ahead?
Yes, please.
Okay, thank you, Alex. I think the first thing I want to say is that I'm well aware that many of you out there are friends of mine, and it's very strange to know that I'm looking at hundreds of friends and not be able to see you. So hello to all of you, and also to those I don't know, of course. And also I want to say that this seminar series has really been extraordinary, and it's just fantastic how it's been put together. So I'm sure many of you have seen most of them, as I have. So thanks to Melina and Stefan and Daniel and Jörg and Valeria and Alex and Bart. The seven of you have really done something extraordinary. And I think all of us in numerical linear algebra, when we look back on this weird year, we will remember this seminar series, and what a nice thing it was. So thank you. Now about the talk. So this is a talk really with only one idea in it, and it's not even a new idea. And so it's a little embarrassing perhaps to be delivering such a thing. But it is, however, a very good and important idea, and one that should be part of our toolkit. So I hope you'll agree with me by the end. You all know the words, you know Vandermonde and Arnoldi. This is joint work with Pablo Brubeck. He's a first-year PhD student at Oxford. Pablo's from Monterrey in Mexico, and he's also spent a couple of years in Illinois working with Paul Fisher at University of Illinois. And Yuji Nakatsukasa is a winner of the Householder Prize, and so therefore, by definition, he needs no introduction in this crowd. But he's a faculty member, normally down the hall from me at Oxford. Okay, so let's begin. The talk will be just a few pages of a little bit of mathematics, and then 8 examples. So to begin with the mathematics, with the heading Vandermonde, you see there P, a polynomial of degree n. And as I presume you all know, a Vandermonde matrix is a matrix set up for dealing with polynomials like that. And I've shown the matrix in 2 different modes here, the solve and then the evaluate mode. So first of all, we see an equation of the form A times C is approximately equal to F. That's the equation where we're trying to find the coefficient vector C. If the matrix is square, it's an interpolation problem. And if the matrix is rectangular with more rows than columns, we view it as a least squares problem. So each column of the matrix is a sample of x to the 0, to the 1, to the 2, and so on up to x to the n in a set of points. And the notation I'm using here is that you have little m points. So if little m is equal to n plus 1, you have a square interpolation problem. If little m is bigger, you have a least squares problem. So this is a very old concept to find a vector C. In MATLAB, it is what is effectively done with polyfit. If you try to write this program in the original MATLAB, it would be more complicated. But nowadays, things are so slick that with operator expansion, all you need are these 3 lines of MATLAB to get the vector C. This, of course, isn't exactly what MATLAB does, but it's the essence of the matter. And by the way, let me mention that we have all grown up with backslash as a notation, which means solve a system when it's square or do least squares if it's rectangular. That was one of Moeller's many innovations when he introduced MATLAB years ago. And in this whole talk, I'm always in that mode, the same formulas, whether or not the problem is square or rectangular. So you solve for this vector C, and then you want to use the vector to evaluate your polynomial. And of course, in principle, that can be at a completely different set of points. So I call that capital M points S sub 1 through S sub capital M. To evaluate your polynomial, you want to compute a matrix vector product. You know the vector, it's the vector of coefficients, but now it's a new matrix, a new Vandermonde matrix, potentially sampled at different points. And this is polyval in MATLAB language. And these have been around since the late 70s, I think. So polyval and polyfit are older than 80% of this audience. Once again, it's very slick in current syntax. So all you need are these 4 lines to do polyval. Now, as you'll see in our applications, I'm particularly interested in the rectangular case. And I think, in fact, that has become more important in recent years. Interpolation is somehow not a central numerical technique the way fitting is. And these days, especially as we have larger and larger data sets and more varieties of compression of data, fitting is almost always what we're interested in. And you'll see as I do the examples. So that's it for Vandermonde matrices. And now I have a slide on monomials. So no linear algebra on this page. Now, you probably know that the monomials 1x, x squared, and so on form an ill-conditioned basis. That's not true on the unit disk, but it's true on any domain other than the disk. And in particular, on the unit interval -1, 1, this is an exponentially ill-conditioned basis, meaning that as the degree goes up, the condition number increases exponentially. So I actually want to do some MATLAB demos. Most of you have never seen me give a talk without a MATLAB demo, and this doesn't seem a good occasion to start, so let's give it a try. There we are talking to MATLAB. And what I'm going to do is just type in the commands that you see there. So as I hope you know, Trefethen is the continuous analog of MATLAB with all the usual commands overloaded for continuous analogs. So let's construct, first of all, the variable x on the unit interval. And let's ask, what is the condition number of x to the 0:10? Now, before I press return, let me just explain what that means. We're looking for the condition number of a matrix, which instead of being fully discrete is continuous times discrete. So it has dimensions, if you like, infinity by 11, or if you prefer, continuous by 11. So that matrix consists of 11 functions, but the condition number of that set is perfectly well defined, and Trefethen will compute it, and the answer is 3000. So even though the degree is only 10, you can see 3 digits of ill condition. If we increase the degree, it increases exponentially. So if we go up to the condition number of the continuous Vandermonde matrix of degree 40, it's 10 to the 14th. Now, of course, you could do discrete analogs of this. So let's do that. Let's take a lot of points in the unit interval, and I'll do that with the Cheb points command. So I've now got 1000 Chebyshev points. And with the same syntax, I could say, what's the condition number of x to the 0 colon 10? And that's now a 1000 by 11 matrix. And the condition number is more or less what we saw for the continuous case. Similarly, if we increase 1000 by 21 or 1000 by 41, you can see that the condition numbers are more or less what we saw before. And in fact, it's known how these things behave asymptotically. Walter Gauci, who I think is in the audience today, proved years ago that the condition numbers look like 1 plus the square root of 2 to the n. So if I, in fact, say 1 plus square root of 2 to the 40, I should get approximately 10 to the 15th. Sure enough. There's one other command there I notice I didn't execute, which is to plot. So suppose I say plot of x to the 0 to 40. So x to the 0 to 40 is a continuous by 41 quasi-matrix. If I plot it, that means plot the 41 columns of that quasi-matrix. And there they are. You can see that they don't look in the least bit independent. They're highly dependent. So, of course, you can't see the condition number in the picture, but loosely speaking, they all look the same, or at least the higher degree monomials all look the same. Which brings me to the second half of this page of the PowerPoint. So a beautiful aspect of the ill conditioning of monomials is this fact that x to the n does not have degree n. Of course it does mathematically, but numerically x to the n for large n has degree on the order of the square root of n. This is one memorable aspect of the ill conditioning of the monomial basis. There's theory about this by Newman and Rivlin in 1976. And let's illustrate that in MATLAB. So here we are again with Trefethen. Suppose I say length of x to the 10. Now what that means is Trefethen is constructing a function, a Trefethen corresponding to x to the 10. It's a polynomial that matches x to the 10 to the machine precision. And the question is, what's its length, which is one more than its degree? Well, its degree is 10, its length is 11. That's the number of points you need to interpolate through to get x to the 10th. What's the degree of x to the 20? 20. What's the degree of x to the 40? 40. Of course, mathematically, it would always be like that, but numerically, once you get above 60 or 70, the degree doesn't increase at the same rate. So x to the 80 is a polynomial of degree 68 in machine precision. And let's keep going. Let's say, what about x to the 1000? Well, that's a polynomial of degree 250 in Trefethen. I said it goes with the square root. So suppose I say x to the 4000. Then that should approximately double the numerical degree. And sure enough, it does. Or x to the 16,000 approximately doubles the numerical degree. So there you see these two different aspects of the ill conditioning of monomials on the unit interval. And I won't talk about the Munz-Sass theorem, but that's a beautiful result in this same direction. Okay, now for the third of my mathematical topics, let's say a word about Arnoldi. And I assume in this audience, wonderfully, you all know what Arnoldi is. Some of you may not. I won't say in any detail, but I'll give the essential idea. So the problem we've identified is that if you work with the basis of monomials, you have terrible ill conditioning. And in practice, if n is much bigger than 30, you probably won't get the results you want. So the solution, and this is the one idea of the talk, is to notice that the monomials are just the kind of Krylov sequence that we're used to when we study Arnoldi and conjugate gradients and so on. So 1x, x squared, and so on is, if you like, a vector or a function. And then that function times a, where a is multiplying by x. It's the continuous analog of a diagonal matrix, if you like. Every time you multiply by x, it's just like multiplying by a matrix A, which happens to be diagonal. So this is a very elementary observation. And the reason it's worth making is that by an accident of history, all of us in this crowd are very good at Arnoldi, whereas we're often not as good at talking about polynomials. So use your Arnoldi skills and think, how would I work numerically with this set of functions? Well, of course, I would orthogonalize at every step. So that is the Arnoldi idea. Instead of forming powers and then orthogonalizing, you do it step by step. You orthogonalize and then bring in the next multiplication by A. Orthogonalize, bring in the next multiplication by A, and so on. That's something we all know, I think. Now, if you apply that to monomials, it's not a new idea. It was invented by Stokes, I suppose. It's called Stokes orthogonalization. So that is what this talk is about. It's the Stokes process. Many, many people have surely done it over the years. This is a list of some of them, but surely it's a small subset. Anthony Austin and friends, Timo Bethke, Bjork and Pereira wrote a classic paper on Vandermonde, George Forsyth in the old days. Walter Gauci is really the great expert on orthogonal polynomials, and he's been involved both with theory and computation for many years. Grag, Hockman, Reichel, Saad, I'm sure some of you are listening. Let me mention Nikos Stylianopoulos in Cyprus. To my mind, is the person who's focused on this most evocatively as an important technique. So it was really wonderful to run into his papers about this. But many people have done this over the years. But, well, you'll see in the examples, I hope the examples will surprise you at how widespread this applicability is. But to try to put it in words, I think anyone who tries to construct orthogonal polynomials runs across the Stokes orthogonalization idea. It's in that territory. It's a standard idea. But what's missing is we don't always notice this when we're just using polynomials. Most of us, when we're using polynomials, don't think we're in the business of constructing orthogonal ones, and somehow we overlook this idea. So one more slide about Arnoldi. So as I say, if you do the Arnoldi process or the Stokes process applied to powers of x, what you're effectively doing is constructing orthogonal polynomials with respect to the discrete measure on the set of sample points. So we could say discrete orthogonal polynomials. And as we linear algebra people know very well, the matrix side of that is going to involve the Hessenberg matrix because of the orthogonalization step by step. And when you work with this computationally, that means you're going to have to pass around this matrix H in your files. So here's how we write our codes in their simplest forms. Instead of polyfit, we have polyfit A for Arnoldi. And as an output, polyfit A produces not only a vector D, but also a Hessenberg matrix. The code, you can look at it, looks pretty familiar, and there are no surprises there. It's doing just what you think. To evaluate, again, we need the Hessenberg matrix because we're working between two different bases in effect. But if you have that Hessenberg matrix, you can evaluate your polynomial at an arbitrary set of points. So here again, there are no fundamental surprises. The codes are just what you would write if you sat down. You wouldn't do it in 10 minutes, I can assure you, but in an hour you get these codes. So those are the fundamental operations we're going to work with, polyfit A and polyval A. If you look at their complexity, you find that polyfit A is O of mn squared. So that's the number of sample points times the square of the degree. And that's the same as polyfit, although the constant is worse. If you look at polyval, the complexity is O of capital M n squared. So that's the number of sample points times the square of the degree. And that's worse than polyval. So polyval A is slower than polyval. Here n is the degree and little m and big M are as before. I should point out that there is a case in which everything symmetrizes and you can use Landshaws. So amazingly, if you have real sample points and you exploit the symmetry, then in principle, you end up with something faster than the usual Vandermonde approach. Of course, there are fast Vandermonde algorithms. But we haven't done that because there are always stability issues, and we're trying to focus on the mathematical essence of the matter rather than minimize the flop count. So all of the experiments I'm showing you, even when Landshaws could have been used, we haven't done. Okay, Alex, I don't know if we're going to have any questions in the middle, and indeed, I don't know if anyone has set up any questions, but if you'd like to interrupt me, now is a pretty good time. Would you like to?
Bart or Daniel, are there any questions on Zoom or YouTube?
Not on Zoom for the moment.
Okay.
No questions so far on YouTube.
So they're all asleep.
Oh, I know. There is one question now in Zoom. For the Helmholtz equation, Brian asks, I don't know who Brian is, no last name. Bessel functions are analogous to monomials. Do you have any thoughts on adapting this idea to the Helmholtz problem?
That's a wonderful question. And of course, you're way ahead of me. You're at least 9 examples beyond this talk already. I certainly think that it must be doable. We haven't really worked on that yet, but I agree with you. The analogy is a very close one. So yes, it must work.
And the person asking was Brian Fitzpatrick from KU Leuven.
Oh, you're saying that's who that was?
Yes.
Yeah, okay. Thank you, Brian. Anything else?
No, that's it.
Okay. So let me now turn to my examples, which is the rest of the talk. So there are 8 of them, and they're all approximately in the same format. In each case, I'm going to solve a problem that involves a polynomial in the obvious Vandermonde way, and then show you what happens if we introduce Arnoldi. So we'll begin with interpolation, not least squares, but truly interpolation of the famous Runge function 1 over 1 plus 25x squared on the unit interval in Chebyshev points. So this is a well-conditioned problem. A lot is known about its conditioning. It's a good problem. Suppose we want to compute those interpolants. The reason for the caption at the bottom here is I've copied that from the paper. But anyway, the point is you see a pair of plots there. The first plot shows the interpolant for degree 80 computed with backslash. And I hope you can see that it's very bad near the boundary. It rapidly becomes far worse. We had to pick 80 to get a degree where the badness was just beginning to set in. So without Arnoldi, you can't get up to degree 80 successfully. It's very interesting to look at this picture of the convergence as a function of the degree. You notice that it goes down to about degree 45 with steady exponential improvement. And then it doesn't merely stagnate, it actually gets a few orders of magnitude worse. Rather fascinating. This kind of thing is something that Ben Adcock and Van Huybrechts have been interested in, the regularization aspects of backslash. What's going on here is regularization of some sort, and the details change in interesting ways once you pass a stability threshold. But anyway, that's all in the details. Whatever method you use, it's going to fall apart at about degree 40 or 50, as you can see there. Now let's run the same thing, but instead of polyfit and polyval, we use polyfit A and polyval A. Then you get, obviously, graphic accuracy, but indeed, you're getting 15 digits. So it goes down to 15 digits of accuracy and then stagnates. It's interesting that, as Alex mentioned in the introduction, I've been interested in polynomial interpolation for a while. There are lots of unstable ways to compute polynomial interpolants. There's also the beautiful stable method of barycentric interpolation. With this problem, you could certainly have done that. The point of this lecture is that the Arnoldi idea is a much more general one that you can easily apply in all kinds of contexts. even if barocentric methods aren't going to help. Okay, so let's turn to the second example. Now this time we're going to do least squares rather than interpolation, and we're going to do it on a more complicated domain, namely the union of two intervals. So we're fitting the sine function, which has a jump in it, which is one of Yuji Nakatsukasa's favorite functions, and we're going to fit that by a polynomial in the least squares sense. So if you like, there's a fitting region and then a don't care region and then another fitting region. If you do that, the picture shows degree 80 and it looks fine. You can't tell that there's any problem graphically. In fact, it gets about 5 digits of accuracy and then it very cleanly stagnates. If you turn on Arnoldi, it goes down and stagnates at the 15th digit at degree 100. This would be a prototype of fitting problems on disjoint domains on the real axis or more generally on the complex plane. So implicitly, we're constructing orthogonal polynomials on this set consisting of two intervals. Okay, the third example is more colorful. So here we have a minimal polynomial of a sort, and I guess we got the idea of looking at these from Alex. Thank you, Alex. The idea is you have a set in the complex plane, and here the set is a triangle. So there you see the triangle in white. And you want to find a polynomial of a specified degree, which is minimal on that triangle, while satisfying a normalization condition. So here the normalization condition is P of 0 equals 1. And this is, if you like, the GM-res condition. It's the condition you would apply in doing iterative solution of AX equals B. So if we were trying to design the ideal degree 30 iteration for a normal matrix whose spectrum lay in that triangle, this would be that problem. These are called Chebyshev polynomials, and that idea goes back to George Faber about 100 years ago. Chebyshev polynomials on an arbitrary domain. Now, the way we've got it set up here, and this is Yuji's work, is to use the Lawson algorithm. So there's some very nice stuff happening here. We want a minimal polynomial actually in the infinity norm on this triangle. It's easy to get close with least squares, assuming you have a good basis. And then once you're close, you can adjust the coefficients with an iteratively reweighted least squares. And that iterative reweighting process is called Lawson's algorithm. It goes back to Chuck Lawson in 1961. So here we've done that. And with degree 30, the instabilities kill you. But if you turn on Arnoldi, it works beautifully. So first, let's talk about this picture. You can see that inside the triangle, everything is blue, which means the size of the polynomial is 10 to the minus 10 or less, or actually it's 10 to the minus 9 or less. And then you have this nice, elegant stuff happening out to this point where it passes through the origin, and that contour marks magnitude 1 because the polynomial has to be 1 at the origin. So that picture shows that it's pretty good. And then this is the more beautiful picture to the aficionados. It shows what we would call the error curve, but the curve of P of Z on the boundary of the triangle. It winds around 31 times, and it's essentially a circle, not exactly, but more or less a circle, apart from the 3 points where it has to preserve these angles of the triangle. And that circularity effect is evidence that we have the minimal polynomial in the infinity norm. So I think any of you who know Yuji know that he's very, very quick. And I think he computed this example during one of the talks at a seminar last December at the Isaac Newton Institute. So thank you, Yuji. I mentioned Adcock and Huybrechts, and this example comes from them. So they have been interested in problems of frames, fitting with redundant bases or ill-conditioned bases, And this example is one of the problems they treat in that setting. They call it Fourier extension. There are various names for it. So this is a very interesting general technique, which has been used by various people in PDE applications. Oscar Bruno at Caltech is very well known for applications of this kind of method. So what we have here is the idea of approximating a function on a domain by Fourier series that live on a larger domain. So here, I have this function on -1, 1, and I want to approximate it by a Fourier series that lives on -2, 2. So it's redundant, it's terribly ill-conditioned. The reason for doing that is that, well, first of all, I can treat a non-periodic function. But second of all, I could think about higher dimensional extensions where it wouldn't just be an interval, but a complicated domain. So suppose we want to fit this function in the white territory by a Fourier series that lives on -2, 2. To plotting accuracy, it looks fine. So there's the fit with degree 40 Fourier series. And here's the convergence. Now, and these ideas come from Adcock and Neubrecht's. It's very interesting. As I mentioned in an earlier example, if you don't regularize effectively, all hell can rather quickly break loose with these problems. But backslash in MATLAB is a very nice regularizing tool, and rather easily by using backslash, you can get this kind of convergence. Now, what's happening here is that in the early phase, it's exponential. But then there's an ill conditioning that sets in, which is being regularized away. And when you mix those two together, you find that the convergence is root exponential. So it converges at the rate of e to the minus constant times the square root of n. So that's why you see this parabolic shape on a log axis. So that is what I would call the Vandermonde approach. Now, the reason for saying that is whenever you use a Fourier series with e to the ik theta, well, e to the ik theta is the kth power of e to the I theta. So a Fourier series is pretty much the same as a polynomial if you change variables. And in particular, if you change from theta to z, you find that this Fourier extension problem amounts to trying to use the monomials to do a fit on half of the unit circle. So normal Fourier series is a monomial on the whole unit circle, but this Fourier extension is a monomial on half the unit circle. So as I said earlier, the monomials are an exponentially bad basis on any subset of the unit circle, except the whole thing. And that's why you have this ill conditioning effect. But now if we turn on Arnoldi, that goes away. So with Arnoldi, you get exponential convergence. There's still a bit of a kink here, so there's some subtleties, I'm sure, but you get exponential convergence down to about 14 digits. So we were really delighted when we saw how nicely that went. It's an example where in one dimension where it almost seems there are no drawbacks to doing this. If you do the same in 2 dimensions, then the slowness of the process becomes an issue, and we're interested. So let's talk about 2 dimensions. So suppose you wanted to fit on a 2-dimensional domain using this Fourier extension kind of idea. Now, actually, this example isn't Fourier, it's polynomial, but it could also have been Fourier. We just haven't programmed that up. So imagine you have a starfish with a function defined on it, and you want to fit a smooth function on that starfish by an ill-conditioned basis, a redundant basis. It could be Fourier extension to a larger square, for example. It could simply be polynomials in 2 variables. And this example actually shows you polynomials in 2 variables, x and y. I'm working on this with Yuji Nakatsukasa and Marcus Webb and Jeff Hokanson. Just to say a word about them, Marcus at the University of Manchester worked with Huybrechts and Adcock and others at Leuven for several years. So he's one of the frames guys. And Jeff Hokanson is a postdoc at the University of Colorado with Paul Constantine. And he was, in fact, the person who immediately after we posted our paper on arXiv tried it in 2 dimensions. So thank you, Jeff. So here we're going to fit this function on this domain. We're not using the Lawson iteration, we're just doing least squares. But one of the things on our to-do list is to do the same in the infinity norm with the Lawson iteration. So if I do that without Arnoldi, for this particular function on this particular domain, it stagnates at about 5 digits. Now, incidentally, if you picked a very smooth function, it would get much further. It would probably get to 10 digits. But it stagnates, just as with the last example, if your function doesn't extend analytically to a big square. This particular function has a singularity approximately here. And that singularity outside the domain is what makes the problem particularly susceptible to the ill conditioning. So there you see stagnation. If you turn on Arnoldi, then in this case, I'm embarrassed to say I don't know how far this one gets. I think it gets to 14 digits. I think Marcus found that. But here's a case where the speed is really getting annoying. So this took something like half a minute to compute, and I have a rule that I don't like to go more than 5 seconds. So half a minute annoys me. So speed is certainly something to think about in these multidimensional applications. But in terms of accuracy, it's wonderful. Once again, the stagnation you get without Arnoldi goes away when you use Arnoldi. And on this color scheme, you can see we have 10-digit accuracy throughout the starfish. Okay, the next example is, I think my final 3 examples are all related to partial differential equations. So this is an example of a conformal map. Strangely, it's another starfish, or maybe a blob, a mutilated starfish. Suppose we want to conformally map that domain onto the unit disk. Now, one way to do that is just via a polynomial representation of the Green's function. I won't go into details, but you can do that. It's a very old idea. You can set up a polynomial, there are unknown coefficients, and there's a matching condition on the boundary, which is the boundary condition of your Green's function. The pole of your Green's function is essentially the point in your domain that's being mapped to the origin of the unit disk. So if you do that, you get, for this domain, terrible stagnation. You see it dies after 1 or 2 degrees of digits of accuracy. On the other hand, if you turn on Arnoldi, then it goes down to 13 or 14 digits of accuracy. I'm not sure what's happening there. So really an amazing difference. It takes this technique, which is useless without orthogonalization, and makes it useful. I should pause here and say that this is a perfect example to illustrate how, in some sense, we've all known this forever. Because anyone who works with domains in the complex plane knows that the monomials are a terrible basis. So it's not a new idea not to use monomials on this domain. What's new is that this should just be a routine part of the way linear algebra people solve problems. The other 2 examples more explicitly involve PDEs. So I want to show you briefly what we call the lightning Laplace solver. And this is work with Abhi Gopal, who is a graduate student at Oxford, working with me and also with Gunnar Martinson. So Abhi and I got interested in solving the Laplace equation by means of rational functions. Here's a domain. Whenever you have corners in a domain, you have singularities at the corners. And the idea is to cluster poles of rational functions near those singularities in order to capture the Laplace solution accurately. And in fact, it can be proved that you get root exponential convergence if your poles are exponentially clustered near the singularity. So this is something I've spent a lot of time on in the last couple of years. We call it the lightning Laplace solver, which is not only salesmanship, it's also mathematics, because it's utilizing the same structure of singularities at corners that makes lightning strike objects at corners. So the idea is to solve your Laplace problem with Dirichlet boundary condition. You match that boundary data by the real part of a rational function. And that rational function has fixed poles clustered near the vertices. Now, it is interesting to talk about Arnoldi applied to that, but I'm not going to talk about that. I want to talk about Arnoldi applied to the much more elementary part of the problem, which is all these singularities are very good at nailing the local behavior, the singular behavior, but they don't necessarily get the global behavior, the smooth part of the problem, the easy part of the problem. So we include, along with these poles, a polynomial term. So in fact, our solution is approximated by the real part of a polynomial plus a rational function. The rational function is exotic and fascinating, and the theorems are non-trivial. The polynomial part is trivial and boring. And we completely paid no attention to it for a while. And we kept finding that our computations would get to 10 digits maybe and then stagnate, or at 9 digits or 12 digits. It was hard to get close to machine precision. And eventually, after exhausting every other possibility, we realized that it was just that we weren't handling the polynomial properly. Even though it's an overcomplete basis, so it's an ill-conditioned problem, and we want it to be an ill-conditioned problem in some sense because it's overcomplete. Nevertheless, Arnoldi orthogonalization is crucial. So that's an interesting bit of mindset here. In this new world where we're always want to use ill-conditioned bases, one mustn't make the mistake of assuming that all ill-conditioned bases are equally good or bad. No, some of them, if you haven't orthogonalized properly, are much, much worse. So let me show you. Here's what you get if you solve this problem with our Laplace solver, but you turn off Arnoldi. So here's the syntax. You can give it a polygon by specifying the vertices. You call Laplace. You specify a tolerance if you wish. And normally that would be all you do. But if you say no Arnoldi, it turns off the Arnoldi. So you can see the stagnation. And if I don't turn off Arnoldi, then you can see it converges beautifully, in this case, down to about 13 digits. So that was very satisfying, and that led to this whole project. I want to take 3 minutes and just show you, because I can't resist. So let's go back to MATLAB. And suppose, you can get this stuff from my webpage. Suppose you type Laplace. If I give it one of the built-in examples like this, it will solve a Laplace problem on a corresponding domain. You can see the poles. There's also a polynomial term. By default, it gives you 6 digits of accuracy, but you can change that. And usually if you go up to 10 or so, there's no problem, often more. Just to give you a sense of the kind of fun we have, suppose you want to solve it on the isospectral drum. And Toby Driscoll was the first guy who worked with this shape and numerically as opposed to theoretically. You can see it's solved a problem in 1/3 of a second to 6-digit accuracy, plotted the result. There's a polynomial term. That black dot in the middle is a remnant of when we used to think that the center of the polynomial mattered. Well, now that we're doing Arnoldi, it doesn't matter, but in some sense, our monomials are based at that point, but it no longer matters. Just to show you a couple more examples. If I give it a number, it makes a random polygon with that many vertices. So here in 1/4 of a second, we've solved a Laplace problem on that shape. If I give it a negative number, it makes a random circular polygon with that many vertices. And we also have a code called conf map that does analogous things for the conformal mapping. So here, there's a random polygon. To construct the conformal map onto the disk, it has set up a Laplace problem, which it has solved by this lightning method. The difficult part are all these poles, and the trivial part is the polynomial term, which relies on Arnoldi. Okay, I think I have just one more example. So let me turn to that. So this is Stokes flow. So as you know, probably, Stokes flow is can be formulated in various ways. This is a fluid flow, incompressible fluid flow at Reynolds number 0. So dominated by the viscous terms. One way to formulate it is as a biharmonic equation, so the square of the Laplacian. And one way to solve a biharmonic equation is by means of two analytic functions. That idea goes back to Goursat in, I think, 1898 or something. It's been used a bit over the years, though not as much as one might think. And Pablo, Brubeck, and I are now using that to solve Stokes problems in the plane. So here you have one of his pictures. It's a flow over a step. And you can see that we're using the lightning method. So these are poles of rational functions that are used to approximate both of the analytic functions that arise in this Goursat solution. So those poles are exponentially clustered near each corner. And then we do what needs to be done. We do a least squares problem in appropriate points on the boundary. And we use Arnoldi to handle the polynomial term, because the poles always nail the singularities locally, but they don't always get the global part effectively. So let me show you a couple of pictures. For this particular geometry with that set of poles, if you do it without Arnoldi, it stagnates at about 5 digits. And even that is pretty good. I mean, to get 5 or 6 digits in a fast computation like this is fine. And indeed, even without Arnoldi, notice Pablo has resolved an eddy in the corner. So just to say a word about these beautiful problems. If you have potential flow over a step, which means the Laplace equation, then there aren't any eddies. Everything is one sign, basically. But if you have the Stokes equation, so viscous flow at 0 Reynolds number, biharmonic equation, then you do get these eddies. So what does that mean? Well, there's in this corner of the domain, the fluid is trapped. It's going around slowly in an endless circulation. It's not part of the global flow. So it's a backwater region. And Keith Moffat proved way back when that, in fact, there's an infinite series of these eddies, not just one. There are infinitely many of them, exponentially smaller as you go into the corner. Beautiful fact. Of course, in practice, you would rarely observe too many of them. So here's what happens if you turn on Arnoldi in this problem. As it happens, you get enough more digits that you can resolve the second eddy. And you see how clean it looks. So this is now on the scale of the picture, it's hiding down there somewhere where you can't see it. But obviously the calculation has been successful to about 10 digits. I think for this problem, we get stuck at about 10 digits. So we were kind of delighted. And in fact, if I remember it right, I think Pablo hadn't even looked for the second eddy. And then I told him to see if we already had it, and he looked and we discovered we had already resolved it without trying. Okay, I think that brings me to my conclusion. So that's the end of the examples. And my discussion will be brief and philosophical, or sociological, if you like. So I was trying to summarize, what am I really telling you about this idea, which isn't a new one? Stilches is an old idea. And Stilches is equal to Vandermonde plus Arnoldi. That's good to know, and people don't usually put it that way. But still, Stilches has been there forever. But I think the sociological fact that makes me think it's worth telling you this is that we in this NLA crowd are very good at linear algebra, and most numerical analysts are good at linear algebra. This wasn't true 70 years ago, but now it is true that the numerical world, indeed the applied mathematical world, has reached a really impressive level of expertise at dealing with matrices. And we all know this community going back many, many years to Householder and Golub and so many people has brought that about. By contrast, the numerical community, although it all knows a few things, as I would say, is relatively uninquisitive when it comes to basic questions of approximation. Here's an example. If I were in a room, I would ask you to raise your hand if you had ever seen that message. And everyone who's used MATLAB would probably raise their hand. I don't know exactly how this message has evolved, but my recollection is that it's sort of been there from the beginning. If you do a basic polynomial fit with polyfit, you often see this. The precise computation I've done here is taken from the help polyfit text in MATLAB, except that I've changed the number 1 to the number 6. So if you type help polyfit, it gives you this, a fit of degree 1 to 50 random data points on the integers from 1 to 50. If you change that to a polynomial of degree 6, you get this message. And surely thousands of people over the years have seen this message and been misled into thinking that this problem was somehow a problematic problem. Well, it isn't. It's a perfectly well-conditioned problem. The message says the polynomial is badly conditioned. That isn't true. It's the basis that's badly conditioned. The polynomial is just fine. So I'm not saying this in order to criticize MathWorks at all. This I take as emblematic of how all of us tend to be a little uninquisitive when it comes to issues of approximation. We don't always turn on, we've all taken an approximation theory course in our past, but we don't always reach into that bag of tricks when doing linear algebra. So if I were to summarize it as one pair of statements, it would be this. And I think this is really interesting if you're interested in intellectual history, as it were. So let's think about linear algebra and approximation. These are two parts of mathematics. They're both extremely important to numerical computation. It's very hard to imagine doing almost anything in numerics without linear algebra and without approximation. They're always there. These are as much our foundation as anything. So in some sense, very parallel subjects in principle, if you like. But the way they've developed historically is very different. Linear algebra, maybe 70 years ago, might have been dominated by theorists, but now it's not. Most expertise in linear algebra around the world is people like us. You know, we're the experts. We dominate this field. There's tremendous expertise in numerical linear algebra. Now, if you look at approximation, which interestingly is usually called approximation theory, it's quite the opposite. Of course, there are numerical people, but the literature and the interest is dominated by more theoretical people. And I work in rational approximation, and that's so clear there. There's a very impressive literature, but it's mostly by theoretical people who, you know, they might occasionally do a computation, but that's not their motivation or their focus. Most papers in approximation don't have a picture in them, for example. So you have these two fields which, intellectually speaking, ought to be or could be very parallel, but the way they've evolved historically is very different. And I think that's the reason why I hope it's been worthwhile giving this talk. Just to remind you all who are really on this side mostly, that there's no intellectual justification for not being good at this side too. They're equally foundational to numerical analysis. And I have to end with a bit of an awkward thing. I was going to stop there out of modesty, but the truth is, if you want to learn a little more about approximation, there's a very nice book which I would recommend to you. The new edition came out this year. If you have the old edition, it's got one horse on the cover, but this is now the 4 horsepower extended edition of approximation theory and approximation practice. Okay, thank you very much.
Okay, thank you, Nick, for the talk. We have many questions on Zoom. So in the interest of time, let me make a selection. There are a few about the orthogonalization process in Arnoldi. Jans-Peter Zemke and Shen Yu Hao are both asking whether you would not want to use double orthogonalization, and also how about the partial reorthogonalization?
Yes, those are very good questions. By double, I presume they mean doing it twice?
I think so, yes.
Yeah, there's no doubt sometimes that is a good idea, and this is something Yuji is very interested in. Yes, absolutely. Variations like that may well be worthwhile in all kinds of settings. If I may editorialize, however, that question shows how expert we all are at numerical linear algebra. You know, you're instantly trying to use some pretty fancy stuff there in order to make the problem, the code even better, and that's great. But it's amazing how often we omit the elementary stuff.
Okay, and then Nikhil Sivrastava is asking, how do you discretize the L-infinity norm in your example? And does this iteratively square approach always converge?
Good question. So in terms of discretizing, we don't focus on that. So we're always in the mode of plenty of points, whatever that means. Of course, you can focus on that and ask, how could you optimally discretize to minimize the number of points? Those are very interesting questions. But again, I think the first order question should be the basic one of how do things behave if you have plenty of points. Regarding the convergence of the Lawson iteration, the iteratively reweighted least squares iteration, I think, I'm not an expert on the theory, I think in most of the linear cases, there is a theorem going way back to Rice or something proving convergence. Not for nonlinear cases, just linear ones. But there may be some assumptions there, and I don't remember exactly what the assumptions are.
Okay, Daniel, do you have any questions on Zoom?
In fact, there's only one question I see so far. And this is concerned with the first part, and it's the extension of this Vandermonde Arnoldi approach to multivariate monomials. So if you have monomials in 2 or more variables.
Yes. Thank you for asking that. And although I had an example that mentioned that, I actually didn't say what we do, which was an omission on my part. So in one dimension, you're just multiplying by x. In 2 dimensions, you're multiplying by x and y. So it's as if you have 2 different matrices, A and B. And you want to orthogonalize in some way as you multiply more and more times by both of them. So there are questions, for example, what order should you do it in? Should you do all the A's and then all the B's, or you interleave them? And we don't know answers to that. We've done various things. Let me mention in this context that the paper by Anthony Austin and Sven Leifer and 4 other people whose names I forget, I'm embarrassed, does this very nicely. So there is, to my knowledge, one paper essentially on that subject. And so it's by Anthony Austin et al. And it's on arXiv last December.
Okay, thank you. I don't think there are any more questions right now on YouTube, but probably there are more questions on Zoom now.
Yes, let me ask one about the Laplace solver. There are actually 2, Blanca Ayuso de Dios, probably pronouncing this wrong, sorry. Can you extend this to domains with cusps?
Oh, I think so. Yeah. Oh, sorry, was there more? Yeah.
Yes, also Alex Barnett has a question related to this. In your Stokes problem, why are there poles on the left-hand corners of the pipe domain? Are there singularities there? There shouldn't be, he says.
So the first question about extending to cusps, we haven't actually done that, but I think actually it is straightforward. You just need different local singular functions. So I think that's fine. It's one of those things we keep meaning to do and haven't done. Hello, Alex Barnett. Alex taught me much of what I know about these problems. So these rational functions are examples of the method of particular solutions, if you like. They differ from the usual method of particular or fundamental solutions in that, first of all, you're using rationals rather than monopoles. And secondly, you have this exponentially clustering near singularities. Now, if I understand, Alex is asking, why do we have poles here? And the reason is, you don't have to. You can formulate this as an infinite domain, and that's one of the cool things about rational functions. But we haven't done that for this particular computation. We formulated it on precisely the domain you see, and we used an inflow condition, which I think is mildly singular at these corners, even though physically the flow shouldn't be singular at those corners.
Okay, so maybe let me ask one more from Cleve Mulder. What should the error message say then?
Thank you, Cleve. Hello. Well, maybe that's a very good question. I'm delighted that you've asked. Maybe I'll say that we have been a little bit in communication with MathWorks about this stuff, and they have been doing a little exploration, and I don't think at this point they've come to a clear conclusion of whether or how to make use of this material, but they are aware of it. Well, Cleve, I guess first do no harm would be the principle. So it's not correct that the polynomial is badly conditioned, so I certainly wouldn't say that. You could say this formulation or something is badly conditioned. And you could say, try using another basis or something. I think it would be great if MathWorks had some alternative codes called polyfit A and polyval A that they would point you to as a possible alternative. But there are so many ins and outs to real software that I'm not sure what should be done.
And then maybe to end, Volker Meerman is asking, let me try to find it again. He asked in the very beginning, what would be the difference in using an orthogonal basis in the first place? Would the ill conditioning still show up? Is Arnoldi then a re-orthogonalization?
Right. If you had an orthogonal basis in the first place, you'd be fine. That's all you need. But of course, usually you don't, unless it's a simple domain. Loosely speaking, we know what to do on an interval, use Cheryshev. We know what to do on a disk, use monomials. But on other domains, you have to somehow construct orthogonal bases. Traditionally, people sort of think in terms of doing that and then solving the problem. But my message is no need. Just interleave it with your problem by using Arnoldi.
Okay, so I think that's it. There are many more. Let me take the opportunity to just say to the people that ask the questions that they maybe can email Nick personally, and he will probably be glad to answer them. That's it for Zoom.
Thank you, everybody.
Okay, thank you very much, Nick, for a very entertaining talk. I'm just looking at how I can share my screen, which I think can. Okay, so if you would like to hear more from Nick and more about rational functions, I imagine he's giving the John Neumann lecture at the SciEM annual meeting online.
Alex,
soon.
Can I still be heard? Can you
Yes.
hear me?
Yes, do you know the date and time?
So far as I'm aware, that's not decided. Last I heard from SciEM, they hadn't decided what mode to use, so I don't know. It may be that it'll happen at another meeting in 2027.
Okay, I guess we should look out for that. Thank you everyone for joining. You can see a screen here of the upcoming exciting lectures that we have. Next week will be Martin Gander, and I hope you will join us for that. If not, please have a nice week and stay safe.